In this set of videos, we're going to talk about another kind of function called the logarithmic function. So if we go back and look at our exponential functions, we've mentioned before that you will notice that the graphs all pass the both vertical and horizontal line tests. So this means that exponentials are functions, and more importantly, that they also have a inverse function because they pass that horizontal line test. If you try to find the inverse function though, and go through that regular process of solving by swapping the x's and y's, you actually get sort of stuck because we don't know how to solve equations like that. We haven't learned that yet. So what we have is we create a new method for solving, and this involves using something called logarithmic notation. So the inverse function of an exponential function with base b is called the logarithmic function with base b. So what we're saying here is that exponentials and logs are inverses of each other. So if x is greater than 0 and b is greater than 0 and b is not equal to 1, then y equals log base b x is equivalent to b to the y equals x. And this function here, this log function, is called the logarithmic function with base b. Now, I want to really clarify here that this is sort of new notation. So it's a different way to express an exponent. So the equations y equals log base b of x and b to the y equals x are actually different ways of expressing the same thing. So here, the b's would be the same, the x's would be the same, the y's would be the same. The first one is called the logarithmic form, and the second one is called the exponential form. So what you want to notice is that a logarithm is actually just an exponent. It's sort of like the idea of having a square and a square root, right? In order to understand a square root, we actually need to know what the square value is. And it's the same thing here. So that logarithm is really based directly on the definition for exponential, just like a root is based on the definition for a square or a cube, whatever kind of root you're doing. So they end up being like opposite ways to write that notation, just like we have for roots and squares, we'll say. So for instance, as an example, we know that 4 squared is equal to 16. So this is something that is in the exponential form. So in the log form, your base is the same as the base here. So this is a base and this is a base. So in this case, my base is 4. So it's going to be log to the base of 4. And notice that the answer to a logarithm is y, which is the exponent. So my answer here is going to be the exponent of 2. And then what happens is this is your x value. So in exponential form to log form, we have this. These say the exact same thing. So 4 squared equals 16 is the same statement as log 4, 16 equals 2. And you can see it right here. 4 squared is 16, okay? 4 squared is 16. The base is the same in each case. So the base is both 4. And then your exponent becomes the answer to the logarithm. So this is a new notation. It's a very similar concept to having a square and a square root, where we kind of need the square to understand what a square root is. You need that original definition. And that's what's going on here. We need to know the exponential form to understand how to write it in the log form. And then we can go back and forth between the two. So let's do some practice. So we're going to write each equation in its equivalent exponential form. So here you have the log form and you want the exponential form. So for me, the two things that really help, one is that the base is always the same. So the base in the exponential and the base in the log are going to be the same. So here, that 5 is going to be your base. So it's going to be 5 is my base. And then what happens in the log form, remember the answer is the exponent. So this would be 5 squared. And then the other value is just your other side equals x. Now, this one doesn't ask us to keep simplifying or anything, but obviously if you wanted to, x would now be 25, right? You could actually kind of solve that. But here we're just changing over the forms. So let's try this one. Here, my base is going to be b here. And then the answer is going to be your exponent. So b cubed is equal to 64. And again, we're not solving here, but you could actually solve something like this now, right? If you think about it, 4 cubed is 64. So your answer here would be 4 if you were taking it to that next step. Here, our base is 3. And again, our answer is going to be the exponent. Oh, and I'm sorry, I do have a typo here. I'm missing something. So let's put the y in here. So it should be, we'll do log 3y equals 7 instead. Apologize about that. So there's my base, there's my exponent. So it's going to be 3 to the 7th power is equal to y. Okay, so just going back and forth between these forms, right? And the x could be in any spot, the variable can be in any spot. It doesn't matter. We're using that same kind of form each time. Now let's go the other way. So now we're going to write using the logarithmic form. And again, for me, the base and the exponent are sort of the easiest ones to see. So there's my base. So it's going to be log base 12. And your exponent, remember, is the answer. So equals 2. And then the other value is going to get filled in. So here, my base is b. My exponent is my answer. So it's going to be log base b equals 3, and then that 8 must fill in here. So log base b of 8 equals 3. Here is my base. Here is going to be my exponent. So it's going to be my answer here. So I have log base e equals y, and then the other value gets filled in. Now, we are going to see in a minute, I haven't gotten there just yet, but we are going to see that log base e, excuse me, is a special kind of log. That e is really special. It's used in so many applications. So your natural e here. So we're actually going to learn in a little bit that this is actually the natural log. And instead of writing log base e, we actually just write it as ln to stand for natural log. So another way we're going to learn to write this in a little bit is as ln 9 equals y. All right, let's do a couple more examples here. Okay. Now, when you're evaluating for logs, the most helpful thing I think to start is to set it up with equals y equals x, whatever you want to call your variable on the other side. So that way you can put it into the exponential form. So for us, it's really difficult to understand logs, but it's easy to understand exponentials. We've been working with them before. We've worked with exponents for a really long time. So when you're trying to evaluate or solve for logs, it's often easiest to change it to the exponential form. So I'm going to do that here. Here's my base, right? There's my base. And remember, the answer is the exponent. So it's going to be 2 to the y power is equal to 16. And then now you want to solve this. So think about it. What value or what exponent would give us 16 when it's applied to 2? So let me think. 2 times 2 is 4, times 2 is 8, times 2 again is 16. So if I multiply that 2 4 times, I get 16. So my y here must be 4. So my answer, log 2 of 16, is equal to 4. Here is my base, here is my exponent. So 7y equals 1 over 49. Now this one you may have to think about a little bit. Notice that 1 over 49, well, 49 is 7 squared. And if you have that denominator, that fraction, remember we can write it with a negative exponent. So this is the same thing as having 7 to the negative 2 power. So again, remember that if you have something like a to the negative n, that's the same thing as 1 over a to the n. So we can use negative exponents to write our fractions. So here what happens is that y is negative 2 in this case. So we get that, I'm running out of room here, log 7 of 1 over 49 is equal to negative 2. Here's my base, here's my exponent. So 25 to the y is equal to 5. Well, think about this. The square root of 25, right, is equal to 5. And another way for us to write square roots is to use that fractional exponent. So this is 25 to the 1/2 would be 5. So here my y value is going to be 1/2. So log 25 of 5 is equal to 1/2. So again, another thing to remember is that when you have an nth root, this is a to the 1 over n. So if I have a square root, that square means 2, so it's 1/2 for my exponent. So here my base is 2, my exponent is y. Think of these like little puzzles. The roots don't really help me, but I can write this as an exponent. This would be a 1/5. And notice here that we have the same. So I should have clarified here. So here you have 7 and 7. They're the same, so the y must be negative 2. Here you have 2 and 2. The bases are the same, so the y value must be 1/5 to get those to match. So my log base 2 of the 5th root of 2 is going to be 1/5. Let's do one more thing in this video. I want to talk about some basic log properties, and I apologize, I kind of got a little bit messy over here. But there are 4 log properties. There's actually lots of them, but there's 4 here to start that are really important. And these are them. So here, if you have the log of the same base to the same value next to it, they basically sort of cancel each other out, and you just get the number of 1. The reason this works is because in exponential form, this says b to the first power is equal to b. So b to the first power equals to b, which is true. So if you have the same base and argument here, then the value is just 1. Whatever base you have, if you're using the number 1, the answer is going to be 0. And this is because in the exponent form, anything to the 0 power is 1. That's why that works. These two are about inverses. Remember how inverses undo each other. They sort of cancel each other out here. So when you have log base b to the bx, so you're combining the logs and the exponentials by composition. You're putting one inside the other. They cancel each other out and you get just x. And the same thing works here. So here we're plugging the log function into the exponential. And again, they're going to cancel each other out. Notice that this is different than this one. So here you just have b to b. You don't have the full exponential there. Here you have b and then b to the x. So that is the difference there. So let's evaluate here. So notice I have log base 7 of 7. So this is of this form here, right? There's no x's in this case, it's just numbers. So this is going to just be 1. Here I have a base of 1. So whenever that value here is 1, the answer is going to be 0. It doesn't matter what the base is, as long as it fits. Like I could be doing log base 10, log base 20, doesn't matter. It's still going to be 0 there. For these ones, notice that you have this composition. So you have log base 4 and then 4 to some power, right? This is different. This one didn't have a power. This one has a power. So what happens is all you have left is that power of 5. And then here you have 6 to the log base 6. And again, all you have left is going to be that 9. So this is what's left here, and this is what is left here. So logs and exponentials are inverses. When they have the same base, they have to have the same base. They cancel each other out when you compose them. So all you have left is that extra number or value that's left over there.